Good, good afternoon, everyone. My name is Milton Halem, and I'm going to speak about a dream of Robert Feynman, the inspiration for quantum computing. Um, we call it the Holy Grail of quantum, the follow-on to the next generation of computing. The next, oh. There are essentially two approaches to quantum computing. There's the quantum annealing approach, which essentially is a quantum reflection of simulated annealing, but instead of using temporal fluctuations, it uses quantum fluctuations to reduce to a ground energy state. The second approach to quantum computing is either a gate or some laser ion approach and things like that. But that approach has the problem of assuming that you could really eliminate most of the quantum noise and anything that could affect it. So there's this intermediate step, which is the analog quantum computer, where people make use of gate technology, but they haven't yet developed the capability to moderate or mitigate the quantum noise. So they run with large with large rates of error, and it would take probably orders of magnitude more bits than they actually have as available for that kind of thing. I want to draw your attention to the system that I'm going to be talking about. This is the D-Wave computer. It's located at the NASA Ames Research Center. It's a box 10 feet by 10 feet by 10 feet. It's a computer which contains one chip. That one chip has the more recent one that they just delivered has 2,000 qubits. A qubit is both is a quantum bit, and the rest of the box is nothing more than a refrigerator, which is intended to cool down the temperature on that chip to about, I keep forgetting the exact number, but 0.001 Kelvin, millikelvin, 15 millikelvins. Okay, so you're down at the subatomic level of photons moving. Okay, and the system that they've put together consists of cells. Each cell consists of 8 qubits, 4 by 4, totally connected. And there's something like 12 by 12 such cells, but not every one is working, so you see some missing. The IBM and Google organizations, and I believe Fujitsu, and there's an organization in the Netherlands as well, are building or attempting to build quantum systems as well. And I won't even mention the Chinese effort in quantum computing, but because she's 3 minutes, and I've got 6 more charts. The Chinese have just announced that they're going to set up a $10 billion quantum computing center. Next, okay. So very quickly, why is NASA interested in quantum computing? Well, we're pretty clear that Moore's law has been sort of asymptoting. It's not doubling every 2 years, et cetera. And NASA is now being consumed with data both from its own satellites, but the satellites it's built for NOAA and as well as for other organizations. New element arriving in science today is deep learning, and so we want to be able to use computers to really delve deeply into data analysis to discover new information. The D-Wave quantum computer is the only available operational computer today where you could have access to it 24 hours a day over the entire year. It's stable. It's as stable as any of the other computer products like that you could go to any computing center. And as I just pointed out, a lot of the major computer vendors, Microsoft, Google, Microsoft, IBM, Fujitsu, and others are all rushing to and Intel has even bought themselves a quantum computer site that is trying to develop a quantum computer. But NASA needs to know if quantum computing will become a disruptive mission technology. And we already know that the Chinese have launched a satellite that's already doing quantum communication over distances about 1,000 to 2,000 miles using quantum entanglement. Our approach was to actually see if we can apply quantum computing to a real scientific problem. And the problem that we're trying to apply it to is, can we, given CO2 data, can we infer, using a quantum computer, the CO2, the turbulent flux of CO2 into the land? That's the problem. Inferring turbulence from measurements of surface CO2. So NASA launched a satellite called the Orbiting Carbon Observatory, and it's in July of 2014, and it's still delivering very useful data. In fact, they have an improved version now that they just released. So we have 3.5 years of CO2 data. We have land surface models that take it off, and we have a neural net. Let me go to the last chart, okay? So we've tried to analyze the data, but here is the key chart. We've taken measurements from ground stations of CO2, number of meteorological variables, some long-wave outgoing radiation measurements, and in this top chart, we've looked at we've applied a feed-forward neural net, and we've obtained RMS errors for the training data of about 4.6, and when we make our predictions, it's down to the order of 3.8. We've done similar calculations on the D-Wave at Ames. We've used the same data, the same code. This was a C code. We implemented it on the front end of the D-Wave, and we've gotten very similar results after different epochs. So in conclusion, we've done the first successful test of a feed-forward gradient descent implementation on the D-Wave, and we've compared those results to the Intel i7 cluster. We've incorporated real OCO2 data into the neural net, and we've obtained near-identical inferences. We validated classical computer input versus the D-Wave system. We've had to run it remotely. We did the running from here in Maryland at the University of Maryland, Baltimore County. And every time we send 1,000 representations of the weighting coefficients that are being minimized, we have to wait several seconds for it to reach, and then we have to take the data back and average it. So even remotely using it, we were able to actually do those neural net computations. Anyway, that's it. And sorry I overran.